So we are going to get started. Good afternoon, everyone. I'm Brahmar Mukherjee. I'm the chair of the Biostatistics department, and it's my pleasure to welcome you to our annual tradition or biannual tradition of celebrating a very famous statistician and a wonderful colleague who has really created the culture and history of this department. We are all here because of Rod Little. And so we established a lectureship in his honor, and Lou is going to share more about the history of this lectureship. And also to honor this year's recipient, Professor Murray Davidian, who has been really an iconic presence in my own career. So what I'm going to do is that last year I did all the introduction and all the hard work. As you become more successful as chair, you know that you don't do anything and delegate. So I'm going to just do the welcome, and Lou is going to do the hard work of talking about Murray's scholarly career, because she's also much more qualified than me to talk about causal inference and missing data. And then we are going to hear from Professor Davidian on every statistical problem is a missing data causal inference problem. I think Rod agrees with the sentiment, but I don't think Rod agrees with Murray's approach. So we are going to see if we can see a battle of the two schools of characterizing missing data. And then at the end, we are going to have a little ceremony presenting the award plaque and also have some concluding remarks from Rod. Finally, the most important thing, if you want to jump out of the window, the reception is right there in the Michigan League courtyard. And there will be wine and cheese, and students are welcome. So faculty have been wining and dining since morning. We had a joint research retreat, but whining, maybe, not whining. And so the real wine ceremony is going to begin. But I'm like, this moment is very celebratory because we get to celebrate our department, we get to celebrate Rod, we get to celebrate Marie, but most importantly, we celebrate the joy of being a statistician. So I just wanted to say one or two things about my personal gratitude to Marie. Marie is one of this is taken in JSM 2013. When Marie was ASA president, she trusted me with being the overall program chair for joint statistical meetings. And that was my first foray into professional leadership. So as you can see that Marie and I believe in fashion statements. Any guesses of who is the man in the photo? Jeremy, no. 538. But what is his name? Nate Silver. Good. I am going to give the prize to Jack because Jeremy I silenced. Oh my God! Even cheating going on. I do not know what to say. This is being recorded, by the way. This is going to go on our YouTube. And now we know for Jack and Jeremy who led the collaborations. So I have to. All right. So as a good chair, I also want to show you that this event and many other events are actually possible by generous support from donors like yourself. So last night, I donated this 100000 to the Rod Little Lectureship just to take a screenshot. I did not continue. I don't have that kind of money, but I believe that Rod is worth every bit of money that I have because he has been a seminal influence on my own career. The code number, if you want to donate money, 701427. Please do remember. And this is an actual gift basket. So those of you who are graduating, your responsibility begins here. So the future donors of this lectureship, you are right here. You are going to become faculty and have great careers. Do not forget Michigan Biostatistics. So after the plaque will be presented after the lecture because you have to earn it. And it's going to look like this, and you are going to see that it is right there. Rod is going to present the plaque. With that, I'm going to hand over the floor to our brilliant Associate Chair of Research, Professor Lou Wang, who is going to introduce Murray's distinguished career to you.
Thank you, Brahmar. And good afternoon, everyone. And it's my great pleasure to be here. And first of all, I would like to extend Burma's warm welcome and sincerely express our deepest appreciation and gratitude to all of you who are joining us today. And thank you and welcome to this special day for our department and for the University of Michigan School of Public Health. I would also like to give a shout out to a few people who made this event possible. Mandy, Kyle, Dave, Sabrina, and Nicole. We are so fortunate to have amazing staff in Michigan Biostatistics, and we really appreciate their support over the years, especially for this terrific event. And without them, this is impossible. Thank you all very much. So with all their great support, as Brahma mentioned, this morning we just had a wonderful research retreat jointly with our dear colleagues and friends at Michigan Statistics and our Biostatistics. And now we are here to celebrate the legacy and work of our dear colleague, friend, and mentor, Professor Rod Little, through the presentation of 2022 Rod Little Distinguished Lectureship Award. As all of us know, Professor Little is a research pioneer and thought leader in the field of missing data, Bayesian inference, causal inference, and survey research. As a former chair of the Department of Biostatistics at the University of Michigan for more than a decade, his vision and leadership have shaped the research, training, education, climate, and culture of this department in many fundamental ways. We, as an academic family, are very fortunate and grateful to have him in Michigan Biostat. And this award was named after Professor Little to recognize his extraordinary contribution to the Department of Biostatistics at the University of Michigan and to the broader profession of statistics and biostatistics. So Rod Little Distinguished Lectureship Award was established in 2016 to honor an outstanding scholar with excellent contributions to the field of biostatistics. And this award is given biannually in every even year and is supported by contribution from many friends and alumni of the department, and to whom we are deeply grateful. In 2016, Professor Joe Greenhouse from Carnegie Mellon University was the recipient of this, the very first Rod Little Lectureship. And then in 2018, the lectureship was presented to Professor Scott Zager, another legendary statistician from the Johns Hopkins University. And in 2020, Professor Elizabeth Stewart, Vice Dean of Education, and Professor of Mental Health, Biostatistics, Health Policy, and Management, also from the Johns Hopkins University School of Public Health, has this award. And now it is my great honor and privilege to introduce the recipient of the 2022 Rod Little Lectureship Award, Professor Marie Davidian, J. Stuart Hunter Distinguished Professor from the Department of Statistics, North Carolina State University. Please join me in congratulating Professor Davidian on all of her accomplishments. Professor Davidian received our highest vote among all the faculty members for this award, and she is chosen by our faculty for her excellent research on the longitudinal data analysis, causal inference, precision medicine, and for her exemplary leadership in the profession, and for her dedicated training and mentoring for the next generation. So given that, I think she definitely deserves a second round of applause. Congratulations. Supposedly the fireworks should be animation. All right, so as we all know, Professor Davidian has an illustrious career. Kyle, Brahma, and I, we tried very hard to just fit a glimpse of her career in this one single slide. But as But as you can see, we almost failed. It's just too hard, and we have to sacrifice the font size and also sacrifice the heading space to squeeze only some of her career highlights. And believe me, even with this, we have to drop many other highlights of her career. There are just simply so many accomplishments, achievements, awards, and honors. Marie, like Rod, is one of the most remarkable, creative, thoughtful, and elegant statisticians of our time. Her impact has been profound in both statistics and beyond in our profession. She began her career in North Carolina State as an assistant professor of statistics in 1987, right after she received her PhD in statistics from UNC at Chapel Hill. She moved to Harvard as an associate professor of biostatistics in 1994 and then returned to North Carolina State 2 years later and then became a full professor in 1998, where she has remained there since. Professor Davidian has served for 15 years as the program director and co-director of the Summer Institute of Biostatistics program for the undergraduate students at NC State and Duke. And she directed the Integrated Biostatistical Training for Cardiovascular Disease Research Program for 16 years. And Marie's team is among the original 3 to propose and host the Summer Institute in Biostatistics. With her great efforts to secure several rounds of NIH grant to support the program, they actually have brought hundreds of students of the United States to NC State every year for 6 weeks every summer to learn about biostatistics. And with their inspiration, many of these alumni are now excelling in the field and in the careers of biostatistics. That's amazing. Professor Davidian has made remarkable contributions to our profession with deep engagement in the major professional organizations, including co-founding the very famous workshop for junior researchers at ENAR. So I myself, and I believe many of our junior and mid-career faculty members here in this room, have participated and benefited from these ENAR junior research workshops in our own career. Professor Davidian has also served as the ENAR president in 2004, the American Statistical Association president in 2013, and executive editor for the very prestigious journal Biometrics from 2006 to 2017, 11 years. How amazing is that? So she is absolutely a fantastic researcher in the field of longitudinal data analysis, missing data analysis, causal inference, and precision medicine. Many of her publications, as you can see, got very high citations. And she is a fantastic scholar and educator. And she not only writes tons of highly cited papers, but also organized all her knowledge into textbooks, for which I am always amazed and grateful for the clarity and rigor. Many of you must have read Marie's book here, Longitudinal Data Analysis and Nonlinear Models for the Repeated Measurement Data. When I was teaching our Biostat 650 here, Longitudinal Data Analysis, I also list both books as the highly recommended textbooks. So Marie said, she actually wrote the book Nonlinear Models for Repeated Measurement Data with one of her best friends from graduate school, David. So, dear graduate students, cherish your friendship during your graduate studies, okay? And maybe someday you guys could write paper or book together, and the book will become a treasured gem in the literature, like Marie and David. A couple of years ago, Marie and her colleagues just completed another book, Dynamic Treatment Regimes and the Statistical Methods for the Precision Medicine, which is already becomes very, very popular. And it was one of the, also my required textbook in my course, Causal Inference and Statistical Methods for the Personalized Healthcare. Marie actually shared a picture of Eric, Butch, Shannon, and herself, those authors, celebrating the publication of this book. And do you see that although they're holding the exciting book, and then we can still see the big M in Eric's Michigan t-shirt. So I have to say, go Marie and go blue. I asked Marie to share a few of her favorite publications, and she said, it is very hard, which I totally agree. See, even she knows it's a very hard job, so you can imagine how hard my job is today. Anyway, so after some very careful thoughts, and she picked these papers. Number 1, her paper with Butch on joint modeling of longitudinal and time-to-event data. Marie said Butch did not want to write this paper because he thought no one would be interested. But then she bullied him to do it. Then it turns out this book becomes Butch and Marie's most highly cited paper together. And from this story, I got to say, husbands probably do need to listen to wives. Because wives, their intuitions and senses are always correct. And then Marie shared her paper with Jared Lansford, the stratification and weighting via the propensity score in the estimation of causal treatment effects, which is actually the final paper after Jared's dissertation. And Marie thought it would not go anywhere, so it would be a miracle if it could be even published. But apparently, she underestimated its value. And this paper becomes very famous and popular later on because that paper spelled out the basic potential outcome framework for the causal inference in a way that made it very accessible to both statisticians and epidemiologists. And from this story, I also learned something. Well, never give up your last chapter for your dissertation, students. Always complete the paper, and then submit it right now. And then Marie threw these other 2 papers to me. One is her paper with Min Zhang. Yes, that is our own Min, and her former student. And this paper on improving the efficiency of inferences in randomized clinical trial using auxiliary variables, auxiliary covariates, is part of Min's dissertation. And then the other paper is on the direct estimation approach for optimal treatment regimes in a restricted class, which actually laid out the groundwork for further methodology in dynamic treatment regimes. Marie specifically pointed out the other paper, the leading author, Ba Qun, is Min's brother. And this is also part of Ba Qun's dissertation. So wow, with this, friends, I learned that Min must be Marie's favorite student because Marie not only advised and inspired Min, but also advised and inspired Min's brother. And Marie must love Michigan because she sent her favorite student to Michigan. Anyway, so from the papers she chose, we can see she is a very exemplary and generous mentor. Marie is not only a fantastic researcher, mentor, educator, she is also a fantastic collaborator and dear friend for many of our colleagues in the field, such as Butch, Gert, Sir David Cox, Nate Silver, Susan. And this picture of Marie and Susan actually reminded me how I got to know her. I met Marie in 2006 when my advisors at Harvard, Xihong and Andrea, sent me to a SAMC workshop. And that workshop is on dynamic treatment regimes. And that is the first time I got into this area. And that workshop was organized by Marie and Susan. So that was one of the very first workshops in this topic. And many of us who actually attending this workshop, participated in this workshop, benefited a lot. And we were guided through this research field. And many of us become very active working in this field nowadays. Marie and her leadership indeed inspired our careers and inspired the next generation of statisticians at NC State and beyond. She is a thoughtful statistician, innovative scholar, fantastic researcher, educator, mentor, and you think that's all? No, that's not all. There you go. Marie is also a terrific ballroom dancer, and that's real dance competition. She is also a lovely wife, a sweet sister, and a dear daughter. And with that, let's put our hands together to welcome Professor Marie Davidian. Thank you, Marie, for visiting us, and congratulations on this lectureship. The floor is all yours.
Thank you. Okay. Now, is this working? Yeah. Okay. Thank you, Mandy.
You're welcome.
Yes, and I will second. A great department is only great because it has a great staff. So thank you, Mandy, for all the arrangements, and thank you to you all. Well, I'm just totally humbled and honored to be selected for this lectureship in recognition of one of my idols. Even though we may not agree on approaches all the time, Rod has really done fundamental work in so many areas of statistics, and he's just an incredible inspiration, has been to me, and plus he's just a really great guy. So I'm just really humbled and honored to be selected. So thank you very much. And it's also great to be back in Ann Arbor. I was trying to figure out the last time I was here. I think it's been at least 15 years. So I'm really, really thrilled to be here and see all of you. Anyway, so what I'd like to talk about today, these are my titles. Every statistical problem is a missing data causal inference problem. So, thinking about what I was going to talk about, I thought, obviously, I want to do something that aligns with all of Rod's amazing contributions to our field. And I've just listed some of them here. And of course, two that stand out to me are things that I've also worked in, missing data and causal inference. So the premise of my talk, it's sort of, the foundation of things I've been doing now for maybe 20 years. As in my title, lots of statistical challenges can be cast as missing data or causal inference, or both, problems, even if on the surface they don't seem to be. And taking whatever approach you take, once you've established that connection, can lead to principled and efficient methodology for addressing those problems. And I will say my collaborators, and in particular Butch, my husband, as well as our students, including students in this room, and I have exploited this premise repeatedly in our work. And so what I'd like to do here, I can't tell you about everything we've done, so I've selected just a few of a not so recent and then two more recent examples of doing this. So the background, and this gets to the sort of dual approaches that Rod and I take to missing data problems. So as Lou showed you, I was at NC State and then went to Harvard in 1994. And it was right around that time that Jamie Robbins, Andrea Rudnitsky, and Luping Zhao published this paper, which laid out sort of, this paper is so dense, it's really remarkable what's in that paper. And it laid out the entire framework for how to cast a missing data problem within a semi-parametric theory framework to derive estimators, efficient estimators, consistent estimators for parameters in a semi-parametric model. And so, of course, while I was up at Harvard, I happened to marry this guy. And in fact, that's him about 2 weeks before the pandemic at this huge ballroom dance competition in Asheville, North Carolina. And that's his Latin shirt there. And he specifically said, yes, I could show that picture because he did really well. He got all firsts. But of course, in his age division, he was sometimes uncontested. But I'll tell you, in ballroom dance, you can come in second even without any competition if the judges decide. So he did well. So anyway, Butch really got interested in this paper. I mean, he'd collaborated with Jamie before. And so when we moved to North Carolina State, he, I think, spent a year of his life doing almost nothing but studying this paper. And like I said, there's so much in it that it did take a year. But once he, went through and started understanding it, of course, if you know Butch, he writes notes. Just notes, 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 all handwritten with a fountain pen. And so he started writing up notes, and then we started working with students and started with a little reading group where we would go through the notes and learn the material. And so at the time I was kind of like, this is probably some passing fad, Well, then it turned out that Butch decided to teach a course in it. And I started realizing, this stuff could be pretty useful. So in 2006, I believe, he ended up putting it all in a book. And the way that came about, just a real quick story, John Kimmel, who some of our more senior people in the room may remember, who was an editor for, at the time he was at Springer, contacted Butch and said, I heard you have this set of notes on semi-parametric theory and missing data. Would you be interested in writing a book? And Butch said, well, I don't really do LaTeX. I would have to LaTeX. And so get this. I mean, I wish I'd known this. John said, oh, that's no problem. We'll get someone to LaTeX it for you. And then you can just modify it. And that's what happened. So that's how that book came about. Anyway, over the years, like I said, we use that theory in some of the ways I'm going to talk about to try to address challenges, statistical challenges. And I got to be much more into it, and I came around to the dark side, and I agreed with him. And in fact, I was amazed when a couple of years ago I actually got asked to write a review paper about this subject. So anyway, so that's the background. So like I said, Rod would probably take a different point of view on some of these problems, but I think we can agree that there's room for all sorts of different approaches. I'm talking at the event earlier today, Bayesian, frequentist, whatever. At the end of the day, we're all statisticians and we are out to solve important data analytic problems. Okay, so as far as semi-parametric theory goes, for those of you who are not that familiar with it, and what this theory was all about, in a nutshell, this distills down the main idea of that 1994 paper. If you know how you would estimate a quantity of interest, some parameter of interest in a semi-parametric model, if you had full data, where you might be solving an estimating equation, then the theory tells you how to estimate that quantity based on the observed data that are available under some missingness mechanism. That's the basic gist. And just a point of clarification for those of you not familiar with semi-parametric theory, a semi-parametric model is just a model for the probability distribution that generated the data, where you model part of that distribution parametrically and leave the rest totally unspecified. Okay, so with that background, let me talk about the three problems that I mentioned earlier. This one's an old one. This is, in fact, from Bachoun's thesis, Mint's brother. I guess at Michigan, I really don't have to say a whole lot about dynamic treatment regimes, because I think there's a lot of people in this room who know this better than I do. But for everybody, I'll pretend like those people aren't in the room, and I'll just talk about it from the ground up. So in any event, you've heard precision medicine, precision health. Clinicians in practice often make a series of decisions. So not just a single treatment decision, but maybe a series over the course of a disease or disorder. And there are key points at which those decisions must be made. And there are feasible treatment options from which they can choose at each. And the whole premise of precision medicine is that a patient's characteristics are implicated in which option is best for the patient, which to choose. And so what a treatment regime is basically, it's a framework that formalizes sequential decision making. So it's a set of decision rules, each corresponding to a decision point, and it takes an individual's characteristics as input, and it outputs a recommended treatment option. So it defines sort of like an algorithm for treating a patient. So being a little more formal about it, if we have capital K decision points, so let's think of finite capital K, you might collect baseline information x1, and I know I have a pointer here, so I can use the pointer, x1, and intermediate information between decision k minus 1 and k, say. So you collect all sorts of covariate information, if you will. And you have treatment options in some finite set of treatment options. And I'll use this overbar notation throughout the talk just to summarize something like this. So this is the baseline and then intervening information collected through decision point K. And you can also talk about the history, which of course would be just the baseline information at the time the patient shows up for the first decision point. And then the history at the kth decision point is everything that's come before that, both the baseline, intervening information, and then the treatments that were actually administered. Okay? And so a treatment regime then is comprised of a set of decision rules, which I'll label as D1 through DK, that take the history as input and then output an option in the set of feasible treatment options for that decision point. And I'll summarize a treatment regime as just D. Okay? So here's a toy example just to illustrate. So consider acute leukemia. There's two key decision points. There's actually more than that, but two main ones we'll focus on here just to make it simple. The first thing confronting a clinician is which chemotherapeutic option, induction chemotherapy, should I give to hopefully induce a full or partial remission or a response, just generically. So at decision one, let's just suppose A1 consists of two options. It could consist of more. And X1, the baseline information, would be demographics, medical history, genomics, et cetera, physiologically like white blood cell count, whatever. Then after a certain period of time, bone marrow biopsy to determine remission status, patients deemed to either have responded or not responded. If the patient's responded, the next thing the clinician would like to make a decision on is how to sustain that response. So give a maintenance type therapy. If the patient has not responded, try something else, a salvage therapy. So at decision two, there are, let's just suppose there are two maintenance options, two salvage options, so four possible options, right? And in that intervening period, there may be additional information collected, certainly response status, as well as adverse events, ECOG performance status, white blood cell count, repeat measures of things, whatever. So for the responders, there are only two feasible options, right? The maintenance therapies. For the non-responders, salvage options, right? So that's just an example of the generic on the previous slide. Now, like I said earlier, a regime is an algorithm for treating an individual patient, right? You just follow the rules. So let's consider a regime D and a patient following the rules, right? So at decision one, the patient has some history, which is their baseline information. And that baseline information from the rule would imply a recommended treatment option, call it A1. Okay, so notice that that treatment option is a function of that baseline information. Right? Then at decision two, we're going to choose an option based on the history. The history is the baseline and intervening information between decisions 1 and 2, as well as the previous treatment option. But that previous treatment option was determined based on the baseline information, right? So in fact, the option that is received, call it A2, is a function of X bar 2, because of course X1 is part of X bar 2, right? And so on. Decision 3, again, the choice of treatment option A3 is determined by the history, which can be written equivalently like this. So is a function of all the accumulated covariate information as well as the treatments previously received. But of course, those treatments previously received are based on all that previous information, right? So the point is here is that the options chosen through decision K, I can summarize, this is the notation I'll use, D bar K, X bar K, because at each decision point, the previous covariate information up to the time of that decision point, so X bar K in general, dictates all the treatment options that were given up to that point. Right? Okay, so I can write this notation like this to summarize what gets more and more complicated as you go through the decision points, right? Is everyone okay with that so far? Great. Okay, so I've now set up the problem, at least what a treatment regime is. Now, if you start thinking about it, whenever we talk about treatment, thinking causally, we think about what would be the mean outcome, say, in the population if everyone followed this treatment, right? Everyone received this treatment. Well, it's the same thing here. If you thought about if an individual with baseline history X1 were to follow the rules in regime D, then what would end up happening? Well, they have baseline information X1. Then after following the rule D1, they would have intervening information at the time they reach the second decision point. I'll call X star 2. This is a potential outcome, right? It's the potential information that would arise, right? And similarly, as you continue through all the decision points. So in general, X star K, D bar K minus 1 is that intermediate information that potentially would arise if the individual followed the rules up to that point. And then Y star D is the final outcome that would be achieved. So just like we think causal inference, Y star 1, Y star 0 in the classic two treatment problem, it's the same here for a regime. And the convention is that Y is coded so that larger outcomes are better. Okay, so we'll keep that. Okay, so with that, now I can get to the analogy. With the standard treatment problem, we would, of course, then be interested in the mean outcome if the entire population followed a given regime, D, which in this world is called the value of the regime. It's just the expected value of Y star D. Okay? And an optimal regime, call it D-op, that achieves the maximum possible mean outcome is something that you'd naturally be interested, where the maximum is across all regimes in the class script D of all possible regimes you could ever dream up. Right? So those are things you would naturally be interested in if you were trying to develop regimes and evaluate them. Okay, so how could we go about addressing those questions? Well, how about get some data, right? So the natural data would be this longitudinal set of information, baseline information, treatments actually received at each of the decision points, okay? So right here, and then of course the observed histories would be given in my overbar notation, like this, right? And then finally we would observe the outcome Y. Okay? So if I could get data like those, hopefully I could estimate the value of a regime for any given regime and even estimate an optimal regime. Now where would I get such data? Well, from all the usual sort of observational sources, which of course can be quite messy sometimes, but electronic health records, registries, whatever. Or, and again, I feel kind of stupid actually explaining what a SMART is, a sequential multiple assignment randomized trial in Michigan. But a prospective way of collecting such data would be through a randomized clinical trial, ideally suited. So here for my toy acute leukemia example would be the natural SMART you would do. These R's are points of randomization. You would naturally randomize initially to the 2 chemotherapeutic options and then randomize responders to the maintenance options, non-responders to the salvage options. Right? So however you collect those data, the challenge then, we've now established, if I'm interested in a particular regime D, the thing I'm interested in, the value, is defined in terms of these potential outcomes, the baseline information, and then all these potential variables, right? And I'd like to estimate that quantity based on observed data. So I somehow have to make a connection between the distribution of the potential outcomes and the distribution of the observed data. And so there's a standard set of assumptions that one can make to achieve that. The consistency, sequential randomization, positivity assumption. Sequential randomization just says treatment actually received is independent of the potential outcomes given the past history. Positivity just says there's a positive probability of receiving all the feasible treatments at each decision point. There better be, or else you're never going to be successful doing this. And so the consistency assumption right here, I need some notation. I'll again use that over bar notation. So x bar star k d bar k minus 1 is just everything potential up to that point, right? And here in the observed data world, analogously. Okay? So then the consistency assumption basically says, consistency, also known as SUTVA, encompasses a lot of things, but for our purposes here, an individual following the first k minus 1 rules in my regime D, basically the x's you observe are the same as the x's the individual would have under the rules in the regime, okay? And similarly for the outcome, okay? So your observed intermediate information or outcome are those that you would achieve under following the rules in the regime, okay? Standard assumption. Okay, so with all that set up, I can now tell you what the missing data problem is, okay? Okay, so in particular, it can be established, as we're going to do right here, that kind of making this connection between the observed data and the potential outcomes can be thought of as what in the literature has been called a monotone coarsening problem, but for our purposes, you can think of it as dropout, okay? So suppose we have a particular fixed regime D. Remember, the full data now are my potential outcomes, and I have observed data, right? So I'm going to define a variable D, coarsening variable, and it takes on k plus 1 possible values, and what I get to observe under any value of D is a many-to-one function of the potential outcomes, okay? So in particular, if D is equal to 1, that basically means the treatment you were actually observed to have received isn't the one you should have gotten if you were following the rules, right? So the part of the potential outcomes under my assumptions we actually get to see is only the baseline information, because anything henceforth isn't consistent with having followed the regime. If D equals 2, well, you were consistent in the treatment you received at the first decision, but then you weren't at the second. And so what do I end up getting to see of W star D, the potential outcomes? I get to see the baseline information. And remember, by the consistency assumption, the X2 I actually have is the same as the X2 star, the potential intervening information, under following at least the first rule of D, right? So what I end up actually getting to see in terms of the observed data is X1 and X2. Similarly, D3, the treatments I actually received are consistent with what the rules would have given me through the second decision, but then the third decision, I departed, no longer consistent. So the part of the of the potential outcomes that I actually have here is X star 3 D bar 2, and of course, that is X bar 3 by the consistency assumption. So you can see that as I move through the decision points, I'm getting to see more and more of the potential outcomes up to a certain point, and by the consistency assumption, that information is consistent with the observed data. Okay? And then finally, D equals infinity basically says, you were consistent all the way through, in which case I saw all the potential outcomes, which by the consistency assumption are then the same as the observed information on me, my x's as well as the outcome. Everyone okay with that? Make sense? Okay, so you see, it's like a dropout problem, right? So there's your analogy. And then to set it up, to turn the semi-parametric theory crank, well, under those three assumptions I mentioned earlier, the coarsening or missingness or dropout is at random, okay? So which means that if we define these discrete hazards, so probability of D equal 1, you're not consistent from the get-go, right? That's a function of as a function of the potential outcomes, it depends only on the part of the potential outcomes you actually get to see. So it's at random, missing at random, dropout at random. And everyone knows a hazard is lambda, right? So we call it lambda, but actually it's better to call it 1 minus the probability A1 is equal to D1. So that's what pi D1 is here. And then similarly for general K, it's the same thing. It's the probability D is equal to K, given that you're eligible to, you're still around at K and still consistent, and the potential outcomes depends only on the part of the potential outcomes you actually get to see, which is right here, okay? And I'll call that 1 minus pi dk, pi dk being AK equals dk. And then finally, you can write the probability of at least being consistent with what the regime would have assigned you through decision K as just the product of those pi d's. Okay, so with that, and this is all spelled out in Butch's book, the kinds of estimators that arise as a result from the semi-parametric theory under this coarsening at random are augmented inverse probability weighted estimators. And here I've just written out what would be an attempt to achieve an optimal such estimator. Here, this is a model for those pi dk's. You may know them if you did a SMART, but otherwise, if you've got an observational data source, you have to posit a model for them and estimate it. Okay. Q, this weird Q here, is a model for the expected value of y star d given x bar star d bar k. And that goes right here. That's the optimal choice of a function of x bar k that goes right here, okay? Which again, you would have to posit models for. And there's procedures to do that, which are spelled out in our book, okay? Now, the simple inverse probability weighted estimator just uses the leading term. So you can see it only uses data on individuals who were consistent with the regime all the way through, which could be not a whole lot of people in your data set, right? So it could be very inefficient. So this second so-called augmentation term is trying to capture back information from individuals who are at least consistent part of the way through. Okay? And this might look more familiar to you, those of you who know about this stuff. This is for k equal 2, writing it out solely in terms of the pi d's and getting rid of the d notation. This is what it looks like here. So again, you see the indicator of being consistent with the regime at the first 2 decision points. Okay? And then you have these additional augmentation terms that are trying to capture back information. Okay. Now, an optimal regime. What can you do here? Well, most of all the methods that are out there for estimating an optimal treatment regime, in one way or another, restrict the class of regimes you're searching over, either because you're positing some sort of model. Even if you're trying to be very flexible, you're still restricting the class to whatever sorts of things can be represented by the class of models. Okay? And so with these kinds of estimators for the value of a regime, what one might do is go ahead and explicitly posit a class of regimes. So where the rules are indexed by some parameter eta. Okay? So here I've just got a real simple toy example where the kth rule is basically if there's 2 treatment options coded as 0 and 1, it gives treatment 1 if xk, say, which is a scalar, is greater than this threshold, eta k, and gives the other treatment 0 otherwise. Okay? And then focus on the restricted class. And so you, the data analyst, with your collaborators, would pick the appropriate restricted class. And so then once you've done that, you can estimate an optimal regime by maximizing any one of these estimators, either the simple inverse probability weighted, or if you want to gain efficiency by using that additional information, the augmented estimator in eta. Okay? And this has all been very well studied, and as Lou pointed out, this was actually the subject of Batun's, one of his papers from his dissertation, and is discussed further in our book. And this is a good time to plug the book again. Okay, so in what I've been doing for like the past, 10 years, is working on smarts. And I know here I've got someone who's worked on even more smarts than I have, which is Kelly. And there's several other people I know around this campus who have done tons of smarts. So anyway, this is just my toy smart again. But I've had a real lot of fun designing these studies and analyzing the data, working with collaborators in all sorts of different areas. It's really been fun with people who have gotten really interested in sequential treatment decision making. So really enjoyed that. But in any event, in a SMART, there are what are called the embedded regimes. These are the regimes that are represented in the SMART. So in our toy SMART, one of these regimes would be give chemotherapy 1. If the patient responds, give maintenance 1. Otherwise, if the patient doesn't respond, give salvage 1. And if you go back and look at the picture, you'll see that there will be subjects who were randomized to chemotherapy 1. There will be subjects who responded and got M1. And there will be patients who didn't respond to C1 and got S1. So there will be subjects who are consistent with following that regime. And there are other subjects in addition who would be consistent. Somebody who got chemotherapy 1, responded, and got M1 would be consistent with the regime that assigns non-responders salvage 1, or the other regime that assigns responders salvage 2. And so there are actually 8 such regimes with all the possible combinations embedded in this SMART. Okay. So one of the goals of a SMART, and sometimes it's the primary analysis in some of the ones I've been involved in, is if I index those embedded regimes by L, is to compare the values of the embedded regimes. Okay? So the null hypothesis might be, are they all the same, or is at least one of them different? Okay? Now sometimes there's an additional control regime, which might be like just a standard of care. Those people don't get re-randomized. They get randomized to control, and they just get followed. So another hypothesis of interest might be whether or not the value of an embedded regime is different from that for the control or standard of care, analogous to a multi-arm sort of platform trial. Okay. Now, in any clinical trial, these days, many clinical trials, most clinical trials, I think, certainly the more large and certainly a confirmatory trial, is probably monitored for early stopping, for either efficacy or futility. Okay? And oftentimes there will be planned interim analyses that will take place at certain points along the way. And one, in designing the study, one, takes that into account, designing and computing stopping boundaries, and so on and so forth. And I don't have time to go into all the particulars of interim monitoring, but this is a really standard thing. And so naturally, in fact, some of my collaborators on some of the trials I worked on asked, we want to monitor the trial. Are there, ways to do that in a SMART? And so at the time, I said, no. Nobody's really worked out. Well, it turns out there has been some work on this. This paper by, this is like so incestuous almost, because this is Abdus Wahed and some of his students' paper that just appeared in Biometrics, Biostatistics, I can't remember. But anyway, Wahed was Butch's student, and Kelly was Wahed's student. So Kelly is Butch's granddaughter. In any event, if we just think about that first hypothesis, you might base your estimators for the value of your embedded regimes on, the estimators I talked about. In Wahed's paper, they actually use the inverse probability weighted estimator. Okay? Now, of course, these estimators only use the data from enrolled subjects who've progressed through all capital K decisions and have their outcome ascertained. So at the time of the interim analysis, at study time T, that's on the calendar time scale, right? There will be enrolled subjects already enrolled. But in a SMART, they might be at various points along the way, having not reached all the decisions yet, right? So the question we wondered about was, could you also use the data from enrolled subjects who are still progressing through the decisions to gain efficiency so that you could stop earlier if the evidence warranted it, or with a smaller expected sample size? So that was the question. Okay, so again, turn the semi-parametric crank, pose it as a missing data problem. Okay, so we've already talked about what our full data are, if we could have them, right? So for any of our embedded regimes, say, what are the observed data at the time t of an planned interim analysis? Okay, and suppose we're planning for n total subjects in the trial. So gamma here is just indicator of whether or not you're enrolled at time t. And let's let kappa t be the furthest decision you've reached by time t. Okay? And then delta t is just an indicator of whether or not you've completed the trial. So you have your y actually ascertained. And so this mess right here is just what the observed data would be. So it's really pretty easy. First of all, you have to be enrolled. Then we know how far you've gotten at the time t. And we'll definitely have your baseline information and your first decision treatment received, okay, because that happens at the beginning. And then depending on how far you've gotten, we'll have additional information, right? All the way up to then, we'll know if you've completed or not. And if you've completed, we actually saw your outcome. Okay, now those existing estimators I told you use only data only on subjects who have y observed. I mean, that's how both of those estimators were derived, under the assumption that those are the available observed data. Okay, so what if these are my observed data? Well, again, you can liken it to a monotone coarsening or dropout problem, okay? Where now we're at time t, for a regime D, we can again define a coarsening variable, which now I'll have depend on t. But you've got to be a little more careful about the dropout process, right? So again, dt equals 1, you're not even consistent from the get-go. dt equals 2, you're consistent, but you've only made it to the first decision. You haven't made it to the second decision yet. So that's as far as you've gotten. Decision dt equals 3, you're consistent at the first with what the regime would have given you. You've made it to the second decision, but alas, you got a different treatment from what the regime would have given you. dt4, you were consistent with your first two treatments, but that's as far as we know. That's as far as you've gotten at time t. And so on, okay? All the way through down to the last decision point, dt equals 2k, you're consistent all the way through, but your outcome hasn't been observed yet. And then finally, you're consistent all the way through and outcome is observed. Okay, so you can see that's monotone, non-decreasing sets of information as you move through. So, once again, under the assumptions, the coarsening's at random. So these quantities, these discrete hazards and so on, as functions of all the potential outcomes can be expressed solely in terms of the data observed under the level of coarsening. And so they can be represented in terms of that. And then through these pi dks I defined earlier, and also in terms of these quantities here. So if we consider, which we did in this work for simplicity, that the decision points are all at fixed times, the same for everybody, then it boils down to just needing to know these probabilities as well to determine these things. And again, modeling the pi dks and these conditional expectations, and estimating these quantities, which are here very simple probabilities you can estimate by sample proportions. Okay? One can write out the estimator, which I'm not going to do in general, but here for the case k equal 2. And we'll call this the interim AIPW estimator, because it's for an interim analysis. And if you go back and look, I know I've got all this stuff on these slides, even though I'm not going to go through it all in detail, just so that you can go back later if you found this interesting. You'll see that this estimator looks just like the one if you had all the data, except for the terms in blue, which are inverse weighting to account for the fact that people are sort of censored. They haven't made it all the way through. Okay? So it turned out to be really cool. And so if I have S interim analyses at set of study times, I can obtain the large sample distribution of all the estimators for my capital L embedded regimes. And for, this is the collection of those, the joint distribution of all of them across all time. Okay? Now, luckily, this is what graduate students are for. So we had this wonderful student named Cole. This work, Eric Laber and I proposed this in a grant, and actually a grant, a PO1 grant that we ended up not getting. And Cole was looking around, he wanted to work on something in clinical trials. So we gave him this problem, and in the meantime had submitted this as another grant, and it was just remarkable. I've never seen a student work so fast in my life. He figured all this out. He figured out the joint distributions, how to estimate all the stopping boundaries using all this multivariate integration, blah, blah, blah. It's actually wonderful. So we have the start here of this sort of group sequential methods for interim analysis, trying to take advantage in a SMART of the sort of information, the partial information for individuals who are still progressing through the trial. And the simulations show you can get substantially in terms of efficiency. Okay. So that was pretty neat. And so that paper is, I think, in the early view in biometrics. Okay, well, since I'm on the subject of interim analysis, I'm going to switch gears now. No more SMARTs, no more dynamic treatment regimes. I'd like to talk about another problem that's really pervasive, but really came to Butch's mind attention during the pandemic in a way I'll describe in a second. So in any event, and just consider a conventional clinical trial, 2-arm trial, 2 treatments, active versus control, whatever they are, and you're interested in some treatment effect parameter, okay? So that's your null hypothesis. And here are the data you're going to collect, certainly treatment received and outcome, maybe some covariates. And typically you'd be interested in unconditional treatment effects. So for example, a difference of treatment means for a continuous Y, or a risk difference, binary, okay? A risk ratio, which you could write like this. So beta here is the parameter of interest. Or if you've got an ordinal categorical outcome willing to assume proportional odds, you might be interested in the log odds ratio. So any of those kinds of problems. And you've got a planned sample size of n, and typically, like I said before, monitored for early stopping. Okay. Now, an issue that comes up during monitoring at the time of an interim analysis is that your primary outcome may not be known until after a time lag t. So for example, suppose you're in a study where y is ascertained after some pre-specified follow-up time, say 1 year. Okay. So in that situation, the lag time's the same for everybody, right? It's 1 year. But there are cases where the lag time might be different for different subjects and correlated with the outcome, okay? So what does this mean for the interim analysis? Well, at an interim analysis, at some time t, in the first case here, y is only available for subjects with 1 year follow-up, so those are the data you would use, right? Now, what do you do here? It's a little more complicated. Okay, so there was a pandemic, right? And during that pandemic, as it turns out, I was telling Rod earlier, Butch was actually, he's been on the NIAID, National Institute of Allergy and Infectious Diseases, HIV Therapeutics and Prevention, DSMB, for I think 2 centuries now. I don't know, it just seems like forever. And that body immediately, once active, the public-private partnership active, started running trials, they pivoted to monitoring active trials. And so he started seeing all these trials where there was an ordinal categorical outcome subject to a time lag. Okay? And so here's just an example of one of these. There was a lot of these active master protocols. I forget what DSICO stands for, so don't ask me. And in any event, this was in patients hospitalized with acute respiratory distress syndrome, and they were randomized to an active agent or placebo. This is like a platform trial, so agents would go in and out, and there was a running placebo group. And they were followed for up to 90 days. And so here are the 6 categories. So it's status at 90 days for at least the first 5. At home and off oxygen for at least 77 days. At home and off oxygen for between 49 and 76 days. And so on. Not hospitalized. So these get progressively worse as you go down. But notice for all of the first 5, you would need to have 90 days of follow-up on the person before you would know. Okay. All right. Before you would know what category, except for the last one. You died. The minute you died, we know what your outcome is and we know when it was, right? So the time lag here is the time you died, right? Okay, so why is this a problem? Well, it's not a problem, but you got to be careful, okay? So if I'm at an interanalysis of time t, not all enrolled subjects are obviously followed for 90 days. So for those who have been followed for 90 days, who have 90 days, okay, so their time lag is 90 days, their Y is available, right? Now, of course, for those who died, we know that Y is equal to 6 at the moment they died, right? And obviously then, T and Y are correlated, okay? So the information on category 6 is accumulating more rapidly. So the result. Okay, suppose subject enters at calendar time E, okay, so they're enrolled if E is less than or equal to T, if I'm doing my interim analysis time T, and this CT here is how long they've been on study, okay? So I know their Y if CT is greater than T, right? That's a complete case, right? So if I were to naively base my analysis on all subjects for whom CT is greater than T, it would overrepresent the dead, right? And lead to biased estimation. So people aren't stupid, they realize this. So the typical analysis would be to restrict only to the complete cases who've been on study at least 90 days, including the dead. You would ignore the people who died before 90 days, okay? But you're ignoring partial information on those with CT less than 90, okay? CT is kind of like a censoring variable, right? It censors your time lag, okay? So like any censoring problem, you know, you want to make sure you take appropriate account of the censoring, and you want to take advantage of any partial information. For example, if CT is 45 for a given individual and they're still in the hospital, you immediately know that they could only end up in category 3 or higher. Okay? Okay, so how can I take advantage of that information? So again, this, at the time of a final analysis, these are the data I might have. I'd certainly know when you entered the study, I'd know your X, I'd know your A, I'd know your Y, I'd know your time lag, and maybe there's a bunch of time-dependent covariates that also might have been collected. Now, of course, estimation of beta, I don't need to know when you entered and time-dependent covariates. All I need is your A and your Y, and if I'm doing some sort of conditional inference, conditional on X, I'd need to know your X too, but that's all I'd need to know. But these would be everything that would be available, right? So in estimating any of these treatment effects, based on A, Y, and possibly X, I would solve an estimating equation, typically, those simple problems I showed you earlier. And suppose there are true values of alpha and beta. There may, so alpha is like a nuisance parameter. Beta is the one I'm interested in. Okay? So for example, in our Tasico study, they assumed a proportional odds model. And so I'd be interested in the odds ratio, log odds ratio. And so this estimating function here would look like this. Okay? So that's just to tell you, yeah, these things are known things. Okay, now, many of you, if you've studied semi-parametric theory, but even in your inference courses, you've probably encountered the notion of an influence function. Influence function is just like a rescaled version of the estimating function, right? So that's what I've written here. Okay? So if I know my estimating function, there is a corresponding influence function. And the foundation of the semi-parametric theory is that there's a one-to-one correspondence between estimators and influence functions. So if I can find an influence function, I can figure out an estimating function, okay, that corresponds to it. And in fact, if I know the influence function, I also know this is all in a large sample sense, the sampling variance or covariance matrix of my estimator, okay, as well, because it's a function, it's basically expected value of influence transpose. Okay? So that's what the semi-parametric says. If I can derive influence functions, then for my interim monitoring problem at t, based on the observed data, okay, I would be in business. Well, the semi-parametric theory tells me that if I know the influence function, if I had full data, okay, I can get the influence function based on observed data. Okay, so what are the observed data in this problem? The observed data are, well, first you have to be enrolled. And then I know when you were enrolled. I know your X, I know your A. And I know whether or not your lag time is censored. And if it's not censored, delta equal 1, I know your Y. And I also know your covariate history up until this point, your time-dependent covariate history. And then, of course, there's some assumptions. Well, by randomization, X and A are independent. Here's just the randomization probability. And if I assume that, the entry process is sort of at random, just kind of people moving along. If you don't have that in a clinical trial, you've got bigger problems. Then, in fact, my censoring variable is independent of everything. So I have independent censoring, right? And so NT is the number of people I have available, and I have a full data influence function. So for any of these problems, I know what the full data influence function is. I don't expect you to absorb all this, but it's here for your reference. The theory says the observed data influence functions have this mess of a form right here. There's the full data influence function, inverse weighted, okay, for the people who I do know Y, right? And inverse weighted by this guy right here, which is basically the survival function for the censoring, given that you're already enrolled and your treatment, okay? And then these functions F here and H here are arbitrary functions of their arguments, okay? And so this defines a whole class of influence functions, which corresponds to a whole class of estimators. And these are just what the quantities in here are, which, like I said, I don't expect you to be absorbing right now. So I just want you to take away this important point that I know a full data influence function. I can derive a whole class of estimators through the observed data influence functions. And these terms right here are the so-called, again, augmentation terms that gain you efficiency. Okay? They imply observed data estimating equations, okay, where I estimate all the junk in there. So I've just got all those there. And of course, if I take these functions F and H to be identically equal to 0, I have no augmentation terms, and I'm left with just an inverse probability weighted influence function. Okay, so turns out the theory tells you what the optimal choices of those guys are. Okay? That mess right there is what they are. And so what we did, rather than trying to model these crazy things, we just represented them in terms of flexible basis functions. Okay? And then to actually solve the estimating equations, we developed a two-step algorithm. Okay? One can, from that algorithm, get the estimator for beta as well as an approximate standard error form test statistics, which can be shown to have independent increments, which if you know the group sequential literature, that makes things a lot easier. And thus, group sequential methods taking account of that censoring and the partial information. Okay? And we showed substantial efficiency gains. And so this paper, we have 2 papers and our package with this. So that was actually kind of fun because Butch and I did that trapped in our house during the pandemic. So it was actually kind of fun because I got to program it all, and and we sat there and argued. In our household, arguments are usually about statistics. Okay, so in any event, I'll close with this. So it turned out back in June of 2020, I was telling Rod this story. Butch called to me from his office. We have offices in the upper floor of our house. He says, "Can you come look at this?" And I went, "Okay, whatever." And I walked down, and he showed me an email from Fauci, Anthony S. And it was, and he says, "Is this real or is this some sort of scam?" And I looked at it and said, "Wow." And I looked at the, and there was an attachment. He was scared to open it because I've trained him, don't open attachments. And so, I looked at it, I said, "I think that's real." He was being invited to serve on the Data and Safety Monitoring Board for the vaccine trials, for all the Operation Warp Speed vaccine trials, which was really cool. because he got to see all the data before anyone else did. In fact, he was the statistician who actually presented the results on Zoom, of course this is on Zoom, to Fauci himself, and watched Fauci's jaw go when he told him that the Moderna vaccine had 95% vaccine efficacy. So in any event, we were inspired because we're trapped in our house, remember, talking about all this. And so one of the big things was that the trial obviously was stopped early and all the participants were unblinded and the placebo patients were offered the vaccine. Some actually went and took the Pfizer vaccine instead because their trial ended a week earlier. But in any event, there was this question of how to evaluate the waning of the vaccine efficacy from the trial data under this unblinding. Because once you unblind, you've screwed things up now because you don't have the two comparator groups going parallel anymore. So what we did in this paper is to cast this as a missing data problem. And we've developed a causal framework for it. And it came out in, I guess, last fall in Biometrics, way after anyone cared anymore. But if you're interested, if you found this idea of using this theory and casting things as a missing data problem, that's the paper. So I will conclude by just saying that we've made sort of a cottage industry of this. As Lou pointed out, Min's part of her dissertation way back in 2008, was it? The covariate adjustment work that she did, that was really cool. She was a great student. Was also a case, as she pointed out, of casting that as a missing data problem. And so we took the approach of exploiting semi-parametric theory to address these problems. But I think the key element here is, sometimes thinking about things kind of outside the box, the way we did certainly with those first two problems, can lead you to fruitful ways of developing new methods. And so, like I said, this is the approach we've taken, but I'm sure in whatever you all do, there's plenty of ways to think creatively about your problems from a different perspective as well. So thank you very much. Thank you again for inviting me. I'm just truly honored, and it's really great to be here and to honor Rod, because he's sort of one of the giants of our profession. So I'm very humble. Thank you very much. Oh, and there's a bunch of references.
Thank you so much, Marie. That was a wonderful, fascinating lecture. Any questions for Marie?
Oh, come on. It was all clear. Well, anyway, if anyone does have any questions, because I went through this pretty quickly, but the slides will be shared, obviously. Feel free to email me. But thank you for your attention, and really enjoyed presenting that. I hope you enjoyed it.
So I do have a
something?
question. So,
Oh, see, yeah.
No,
I knew it.
I do have a question because I just want to, for the students in particular, there are different approaches of missing data, and obviously in Michigan we follow one style, but here we saw a very different style, and also we want to have a blend of different styles. Min is in our department, so she does this inverse probability weighting, and
that one does too.
So does Lou. So does a lot of. So we have infusion of different kinds of idea. But what do you think about, when we are training this next generation of statisticians in terms of different schools of thoughts? Because if you want to go deep in one school, then it's hard to embrace the other philosophy. So how do we deepen and broaden our education in terms of competing with existing methods, that section?
Yeah, so like the Bayesian versus frequentist, for example. Yeah. No, I mean, in fact, we were talking about this earlier today at our table. It seems like there's this ever-expanding universe of things we want our students to know, and how do we fit it all in? So that's one issue right there, is how do we do that? But just getting back to the issue of, I just feel like, we all should know something about everything. So, I'm clearly a frequentist, but I have studied Bayesian methods simply because I think it's important, to have a broad perspective, because you never know what you can learn from another way of thinking about problems. And so I feel like we should be training our students somehow, and I don't know how because we've got this limited time, but to make sure they get exposed to different ways of approaching problems, even if they choose, and we choose as faculty, to take the deep dive into a particular area. And the challenge is, how do we do that in the time we have allotted? So I don't know is the short answer. It's very difficult, but I think it's really important. I know when you're working on your dissertation, you have this goal, which is like, I want to get out of here, right? And so I'm going to do what I need to do to, and that's fine, because, you're studying a problem, you're going to be the world's expert on that problem when you're working on your dissertation. And remember that when you're defending your dissertation too. The faculty, you might think, oh, they already know all this stuff. They don't know what you're doing. You know more than they do. Just always keep that in mind. I always tell my students that. Now, we don't know what you know. You know this problem like no one else. So, I feel like, but once you're out, take advantage of whatever you can to learn as much as you can about all sorts of different approaches to things or new areas. Because, even if you're working in a particular set of problems, at least initially in your career, you can learn so much from other points of view and other ways of different problems and the way those are approached. And like in my talk here, see a connection, casting a problem a different way might lead you to a solution. So.
Thank you. And I have just one tiny little question. You presented the general structure of the problems, which was very insightful. But with machine learning and algorithmic modeling and penalized regression, all of these infusing our profession, where in your work do you see that place? And have you used it in the different places when you try to make your models more flexible?
Yes, we have, actually. In fact, an example, again, Bachun, Min's brother, another paper from his dissertation was recognizing, and I know Min's done some work with this too, with Bachun, on recognizing that you can cast, and this was in the case of a dynamic treatment regime, but only with a single decision point. You can actually cast that problem as a classification problem and then use whatever sort of machine learning techniques to what ultimately comes about to represent your regimes. And so and it was just beautiful, and Bachun figured that out. It was just, I was just in awe of that, how elegant it was, beautiful. But yeah, so that was a case where actually once you recognize that connection, you could use any kind of machine learning techniques to actually represent your regimes and come up with an estimate an optimal regime. Yeah. Now, some of these other things, certainly, you can use in any of the modeling that goes into this, you can use whatever kind of flexible models you want. And people study the theory under those kinds of things and as well. At the same time, I know that, and maybe I'm showing my age here in my, excuse my French, but old fartdom, in that, there's so much going on with, machine learning and artificial intelligence and so many things. And then at the end of the day, there's a 2-arm clinical trial going on that, and that's not going to stop. I hope not. I don't think ChatGPT, I don't want to take the drug that ChatGPT told me I should be taking. Okay. I'd like to see some actual evidence from, principled evidence from trials, and certainly I hope pharmaceutical companies continue to do that when they develop drugs. And so there's still a lot of statistical problems out there that, probably can benefit in some ways by, maybe integrating those kinds of things into things. But at the end of the day, some of it might just be our bread and butter stuff that we've been doing for centuries. Maybe not centuries, but we're a young profession, but yeah. So.
Any other questions? If not, I'll invite Professor Little to come on stage or the front of the and present the plaque.
I'll make a couple of remarks before.
Yeah, I saw him writing furiously.
So I'd really like to thank Marie for coming. She has, for giving a very clear lecture, and for her many seminal contributions, both to the theory of missing data and causal inference, but also to the profession in general. So I don't necessarily share exactly the same philosophy as Marie does to statistics, but I do want to say that I think it's extremely important to have different reviews represented and to have intellectual sort of exchanges, friendly intellectual exchanges, respectful intellectual exchanges. Doesn't always happen. I'm reading this book, writing a book a little bit on
Yeah, no kidding.
for example. I think one of the philosophies in our own department is to have representation from both
Yeah.
viewpoints. And my own sort of philosophy of statistics can be summed up in two phrases that I think Bayesians should be frequentists and frequentists should be Bayesians. So.
Yeah, you're right. Totally agree.
Thank Marie for her talk, and I'm very happy to give her a plaque. She gets to check, which is more fun. I think we have a picture.
Oh, wow, with quite in the projecting.
Just thank you. And what do I do?
Oh, you get that.
Oh,
Rod, I stand here. Because
the check. Yeah.
So it's very important to show that while Rod carries the honor of the department, I carry the money. So I am presenting with a fake check, which Kyle created to make it look as fancy as possible, so that Marie can also put this on her wall. And the real check is truly under process. And so thank you so much, Marie. Thank you so much.
zeros.
Yeah.
Few less zeros.
Yeah, can I just add?
No, add on zero. This is not missing data. This is observed. To close the ceremony, and this is a surprise, but I'd really like, we have heard a lot about Mint's work, and I'd really like to Mint to say a few words to close the session. Where? I don't know how to say. This is really a surprise. And yeah, I just so excited, Marie, to have Marie here. So yeah, Marie and both they are like my mother and father. So when I joined NC State in 2004, so actually I didn't have any background in statistics or math. So I was very eager to learn, and I also I was not sure whether I could be a good student. So I think in the first year I took several Marie's class and longitudinal data analysis and also a seminar course. And I remember the first course I took is a longitudinal data analysis and in the midterm. So I think a lot of the question is not like a derivation. It's like you need to write them like an essay to answer those questions. And I remember. So I got 100 in the midterm, and also in the final. I remember. So Marie so she commented in my answer the accent. I was so encouraged, and after I think after 1 year, so I want Marie and we took my advisor. So I approached Marie first, but at that time I haven't
I haven't taken my qualified exam yet. And Marie said, but Marie was very, very kind. She was showing me the paper by the past student. Very encouraging. But he told me, just wait until you pass the qualified exam. And then I did the qualified exam. But then I haven't got the result yet, but I passed or not. Then I sent Marie an email saying, hey, can you be my advisor? But I already took that. And he said, yeah, let's just wait to see. And then I went to California to meet my boyfriend at that time. And I came back. I thought the results were already out. And then I asked Marie again, I said, can you be my advisor? And Marie said, yes, but do you know your school for the qualified? Haven't. Yeah, so I was very eager at that time. So yeah, I was so happy to have Maria and the Bush to find one. I think that the best advisors I can go for. And then yeah, I graduated in 2008, and my brother was trained, so he joined the department in 2006. Right? Yeah, so yeah, I think 2 years after. So but he never asked me who to choose to be advisor. And I never, he never had a discussion. That's I never had. What? I left the state as I came here, and then I know like battery talk to you and the boots they wanted. Yeah, and that's so glad I think we had yeah, I feel like everything I have today is because of Maria, which yeah, I was just so grateful for all the things that you have done for me and my brother.
Oh, wow. Oh,
Yeah, in China. Yeah.
well, thank you. She was a wonderful student.
Oh, okay.